Hello everyone. So after the previous lecture, we have covered these topics. In the first, we started with the bracketing method to optimize our function to find out the range in which the minimum of a function will lie, right? So in the bracketing method, basically what we did was that suppose we have a function, right? We have function fx defined in the range of ab, right? We have a function fx defined in the range of AB, and we need to find out the minima of the function, right? If this is the this x star is the minima of the function, and we need to find out the range in which the minima of the function will lie. So using bracketing methods, what we used to do was we used to reduce our search space. Okay, so in the initially the function was defined in the range of AB, right? The function was defined in the range of AB. So using the bracketing method, what we did was we used to reduce our search space. We used to find out 2 points, let's say x1 and x2, and we used to say that the minima of the function will lie in between x1 and x2. So basically, we have bracketed our minima. We have bracketed our minima. So the methods that we discussed in the bracketing technique was exhaustive search method and bounding phase method, right? After this, we studied about the region elimination method, and in this we started with the discussion of the fundamentals of region elimination method, right? And in region elimination method, using sophisticated algorithms, the range that we have bracketed, right? The range that we have bracketed, that is, we have in the bracketing method we had defined that our function, the minima of the function will lie in the range of x1 and x2. Okay, the minima of the function will lie in the range of x1 and x2. Through the region elimination method, using sophisticated algorithm, now we used to reduce our search space. So using the region elimination method, we used to skew up, or we used to reduce our search space. So now we, through these implementation of these algorithms, we used to define that now the search space is reduced through x3 and x4, right? From x1 x2, now we using region elimination technique, using sophisticated algorithms through the method interval halving method, using Fibonacci search method, using golden section search method, we used to reduce our search space, and then we used to define that yes, the minima of the function fx will now lie in this range x3 and x4, right? So up till now we have covered this, up till now we have covered till here. Okay, now in the methods that we have discussed, only to, we used 2 points to search the region in which the minima of the function will lie. Okay, but the magnitude of the function was not used to define our search space, right? Only the relative function values were taken up, right? So now we are going to study about a technique or a method that will also use the magnitude of the function, and that method is a point estimation method. Okay, so your point estimation method uses the value uses the value and magnitude and magnitude of the point to find the minimum value of x that will minimize the function, that will minimize the function. Okay, so in your point estimation method, we use the value and the magnitude of the function that will help us to give us a more accurate result. One of the technique that we are going to discuss in the point estimation method is successive quadratic estimation method. Okay, so the technique that we are going to study in the point estimation method is successive quadratic estimation method. Okay, so let's discuss about the successive quadratic estimation method. So your successive quadratic estimation method use curve fitting technique, right? So basically, suppose we have our function, right? This is our x, we have function fx, right? We have a function fx. Now using curve fitting technique, what we do is we take a quadratic polynomial function and fit over this curve, right? So we take a quadratic polynomial function. Okay, so let's say this is our quadratic polynomial function, right? And we fit over the curve, and then what we do is we take points over this quadratic function. So let's say this point is intersecting. So let's first of all define it as function qx. This is our function qx. Okay, so we have 3 points, right? And let's say this is x1, this is x2, and this is x3. Okay, and of course for each value of these function on x will give some value of function, right? So this is, let's say, f1, the value here is f2, and let's say this is f3. Okay, this is, let's say, f3. Okay, so in your in this method what we do is we fit a curve, right? We fit a, let us write it down. In your quadratic successive quadratic estimation method, a curve is fitted, a curve is fitted, that is quadratic polynomial function, right? That is quadratic polynomial function. Okay, and any quadratic polynomial function can be defined in 3 points, right? So any quadratic polynomial function can be defined in 3 points. In this case, the points are x1, x2, and x3, which will give 3 function values. Okay, and the algorithm begins with taking these 3 points. Okay, the algorithm begins with begins with begins with taking begin with taking 3 initial points. Okay, and of course this function will also have a minima, right? The this function qx will also have a minima, so we will take this value of this minima, let's say that will be x bar, that we are going to discuss, and through this we progress our search for finding out the minima. All right, so the equation for a general quadratic function passing between 2 points, for this we have an equation, right? So a general quadratic equation, a general quadratic function passing through 2 points, passing through 2 points x1 and x2 can be written as, so this is a general equation for uh, quadratic function passing through 2 points, right? And this equation is qx is equals to a naught plus a1 x minus x1 plus a2 x minus x1 x minus x2. Okay, so this is the general equation, right? So here the x is the variable point, right? It varies based upon the point that you are taking. Okay, so if in this equation, if we take x1, right, in this equation, instead of x, if we put x1, then we will get this function value will be f1, right? Likewise, if we instead of x put x2, then our function value will be f2. Similarly, for if we put x equal to x3, our function value will be f3, right? So if we put these in the equation, we can find out the value of a naught, a1 and a2, right? So let us first of all find out the value of these, right? A naught, a1 and a2. So let's say we are putting, so first of all let us write down, if x comma f1 x1 x2 comma f2 and x3 comma f3 are 3 points, are 3 points on the function, 3 points on the function, right? So putting x equals to x1. Okay, so let us put x equal to x1 in this equation. So in this case our function will become this qx will become f1, right? Our qx will become f1. So your f1 is equals to a naught a1 x minus x1. Here a1 x is x1, right, plus a2 x minus x1 x minus x2. So this will be x1 minus x1 x1 minus x2. Okay, so this will be 0, this will be 0. So in this case your f1 will be a naught. This is the value of a naught. A naught will be equal to f1. Okay, now let us put x equals to x2. Let us put x equal to x2. So our function will become, if we put x2, function will become f2, right? So this will be f2 equals to a naught plus a1 x2 minus x1 plus a2 x2 minus x1 and x2 minus x2. So this will become 0, right? And we have from the equation 1, let's say this is equation 1. So from the equation 1 we have the value of a naught, right? So we'll have f2 minus f1, we'll put the value here and we'll take it here, right? So this will be f2 minus f1 divided by x2 minus x1. Okay, this will give the value of, this will give the value of a1, right? Let's say this is equation 2. Okay, now we will find out, we will put x equals to x3. We will put x equal to x3. So in this case the function will become f3. Okay, so your f3 will be equals to a naught plus a1 x3 minus x1 plus a2 x3 minus x1 and x3 minus x2, right? So we have the value of a1 from equation 1, right? So this will be f3 minus f1 equals to a1 x3 minus x1 plus a2 x3, let me write it down same way, x3 minus x1 and x3 minus x2. Okay, so this will be solving it, f3 minus f1 divided by x3 minus x1 this is f3 minus a1 x3 minus x1, this will give a2 x3 minus x1 into x3 minus x2. Okay, so we will take this into denominator, f3 minus f1 divided by x3 minus x1 x3 minus x2 minus a1 x3 minus x1 divided by x3 minus 1 and x3 minus x2. This will be the value of a2, right? From here we can see, we can cut x3 minus x1 and we have x3 minus x2 common, so we can take it out. Okay, so this will be 1 upon x3 minus x2 f3 minus f1 divided by x3 minus x1 minus a1 will give the value of a2, right? This will give the value of a2. Let's say this is equation 3, this is equation 3. Okay, so what we'll do is, now from the equation 1 and equation 2 and equation 3 we have the value of a1 a0 a1 and a2. Okay, so we will put these value in the in this equation, right? We'll put the value in this equation and we will differentiate it with respect to x. Okay, so through this we will find out the minima of the function. Okay, so putting values of a0 a1 a2 in qx, right, and differentiating with respect to x and setting it equal to 0. Okay, So what we'll do, so through this what we will see in the single variable function when we were discussing, this is how we used to find out the minima of the function, right? So through this we will get, through this we will get minimum of above function. We will get minimum of the above function, which we will denote as x bar. Okay, so your x bar will be equal to x1 plus x2 by 2 minus a1 by 2 a2. Okay, and if your q double, we double differentiate it and this function, and if it is greater than 0, then we find out the minima of the point. Okay, with the condition that a2 should be greater than 0. Okay, so this successive quadratic estimation method basically depend upon three basic points. Depend upon three basic points. Okay, so through this we find out the value of a1, a2, and x bar. Okay, so let us discuss the algorithm. How do we proceed in this method? So in this step 1, we take up the value any value x1, the initial point, and we move ahead in small interval of delta. Okay, and then we compute the next point, that is x2, which is equals to x1 plus delta, and then we find out the value of fx1 and fx2, and if fx1 is greater than fx2, we compute x3, that is the next point, which is equal to x1 plus 2 delta. Okay, and then we find out the function value. Okay, if fx1 is not greater than fx2, what we'll do is we'll take x3 equal to x1 minus delta, and we will evaluate fx3. Okay, so at this point we have 3 points. We have x1 point, right? We have x1 point, we have x2 point, and based upon the situation of this, we either have x3 point through this equation or x3 point through this equation. So basically we have 3 points, x1, x2, and x3, right? And from that we will find out which of these points, x1, x2, or x3, based upon the condition, is giving the minima of the function. All right, and the minima of the function will give the minimum value of that point. Okay, so let's say if our x1 is giving the minima, so our x minimum will be x1. Okay, likewise, if the function value of x2 is is giving the minima of the function, then our x2 will be minimum. Okay, depending upon the function with which we are dealing with. All right, so through this after this we will find out the x bar. Okay, the minimum value, function value of the quadratic polynomial function, right, that we have fitted. So your x bar will be equal to x1 plus x2 by 2 minus a1 by 2 a2. Okay, so a1 value and a2 value we have found in the derivation. So this is the value of a2, and this is the formula for finding out the value of a1. All right, so through this we will find out the value of x bar, and then we will check if our f minima minus f x bar, right? So whatever x bar we have find out, we will also find out the function value of fx bar. All right, so through this we will see if our f minimum and minus fx bar and our x minimum that we have found in the previous step and the x bar in this step is small. If they are small, now small means that the value after decimal places, after one decimal place, the value is coming from 0 point something, all right, or 0.00 something, or after a successive iteration the value is increasing. Okay, so if the value is small, then it's okay. We have find out the optimum value and we'll terminate. If the value is not small, we'll go to step 6, and out of the minimum value we'll take up the best point, and then we will move back to step number 3. Okay, so this is the algorithm for your functioning of successive quadratic estimation method, and to find out the minima of the point using this method. Okay, we are going to discuss about the numerical example of same in the next lecture. Okay, so this is all for today.